lecture 3. Um, so we talked about recovery, recrystallization, and grain growth. So um, recovery is the process by which the material will recover from the stress that is introduced into the material during the cold working or the hot working process. So if you're doing hot working, what happens is that the recovery and recrystallization and even grain growth might happen during the same process by which you are doing during the same process when you are doing the hot working. But in the case of cold working, you have to give it additional energy through heating for making the material adapt to the stress that you have introduced during the cold working process. So what they have seen in many materials is that there is a critical strain that you have to introduce above which only the recrystallization, recovery, and grain growth will occur. Mainly the recovery and the recrystallization will occur. And in the case of alpha brass, it is 5%. So if you look at the handbook, they have done a lot of studies where they have looked at the critical elongation that is required in order to make the recrystallization process go. And what you may also find is that if you are doing certain deformation processes, it can lead to some amount of surface roughness on the sample surfaces when it is exposed to some kind of compressive forces. So for example, you see here the surface roughness on the cylindrical surface of a aluminum sample exposed to compression. So as I said to you, the typical differentiation between hot working and cold working is approximately half the melting point in degrees absolute. So in this case, they are saying that, this textbook claims that cold working is only if it is less than 0.3, warm working is between 0.3 to 0.5, and hot working if it is above 0.6 melting point in degrees absolute. But typical numbers are half the melting point in degrees absolute. And this is the same temperature which takes into account the creep processes that can happen more in an accelerated fashion if you go above that temperature. So T is the operating temperature and Tm is the melting point. Okay. So what happens when you are doing, say, a tensile testing of a ductile sample? So if you have a ductile sample, if you apply a tensile load, they will typically neck before fracturing. But if you do a compressive force on it, what you will probably see is that there is some amount of buckling that will happen during the compressive load. But if you have brittle materials, what happens is that if you apply a compressive load, they do not exactly break in the center. They might break in multiple pieces. And what you will also find is that if you are doing um, a compressive test, or you are applying compression on a ductile sample, before fracture happens, these materials can actually, they will probably do some battling, expansion on the sides. And what you might also find is that there are cracks in the middle of the sample before it starts crumbling. So if you are doing what is upsetting, upsetting is you are applying um, compressive force, um, and if it does not do the barreling, then just the compression by which it expands in a very, very uniform manner, it is called upsetting. And you do that by this, and it applies some amount of friction at the die workpiece interfaces. So if there is barreling, then if there is too much friction forces, then it can introduce some amount of barreling on the sample, and it happens the more ductile the material is, because it makes it easier for the sample to um, deform by the barreling process. So what are the different types of fracture that can happen if you are applying a tensile load? So if you have a polycrystalline metal, it can happen, it can fracture in the middle with very little ductility. So if you have a ductile single crystal material, um, it can fracture by the some amount of shear failure that is happening in the middle of the sample. If you have a polycrystalline metal which is very ductile, then it can fracture. First, it starts creating some amount of um, voids during the tensile failure process, and they will all start joining in, start necking, and fail. So this will happen if the material is extremely ductile. Say for example, if you have gold or silver or copper, something like that, they will all fail in this manner. But if you have, say, iron or something like that, it might fail in this manner or in this manner. So what are the original and final shape? I mean, if you recall from your tensile test that you guys did in ENSA 3313, you will find is that you start with the original gauge length, and after failure it will extend to an additional length LC. So this is L0 and this is L1 or LC, and you can correlate that to the stress strain curve of your sample. So if you are deforming the material, you will try to stick in this region rather than go beyond that, because if you go beyond that, it is going to be failing rather than deforming. So different materials will deform in different manners. So for example, in the case of low carbon steel, um, if you look at the fracture surface itself, you will see that there are a lot of dimples, and these dimples are formed during the failure process itself, and they will all start link up, and uh, as the material starts detaching from one side to the other, then the sample is held together only at the edges of these dimples, and they no longer can take the load, and beyond a certain limit those dimples will start detaching and start failing. And the fracture is usually initiated at impurities or inclusions or pre-existing voids. Uh, but sometimes you will also find that the sample will um, there were no pre-existing voids or impurities, but they will still fail in this manner. I mean, if it is a ductile material. So when you are applying a tensile load on a ductile material, they will start elongating in the middle of the sample. Then it will start, when it starts elongating, the cross-sectional area starts reducing. It starts forming small voids, and those voids will start linking up. And then here at this point, your sample is only held together in a couple of different places, so which means that that area which is holding that load or withstanding that load is no longer capable of taking the entire load, which means that beyond a certain limit, that material will give way and break into two pieces. And this is typically called a cup and cone fracture. And when you start putting them together, you can see that they will both match with each other. Again, for the purposes of the manufacturing process class, what you need to understand is that when you want to do a manufacturing process, you try to limit yourself to the area from the elastic limit to the maximum tensile stress. You do not go beyond this limit. If you go beyond this limit, you have already damaged the entire component material. So if you limit yourself in this area, then you can deform this material into different shapes and forms. Okay, so continuing further, so this is if you had the material that is perfect and no inclusions or no impurities and things like that. If you have impurities and inclusions, then the failure can happen in a much easier form. So those inclusions and impurities can act as the initiation points because they do not have the same properties as the original material itself, and then they can start linking up and start initiating and cracking at those points. Okay, so the whole material will fail at a much lower stress than compared to a material with no such impurities and inclusions. Now, we also talked about ductile to brittle transition temperatures. So, what is the correlation between the ductile to brittle transition temperature and a manufacturing process? So, if you are below the transition temperature, that means the material is brittle. So, which means that if you are trying to manufacture a component, you try to be above this temperature, because otherwise the material is going to fail in a brittle manner, and it can easily fail in a non-predictable manner. So you do not want that to happen. So if your material has got a clear ductile to brittle transition temperature, you want to be above that temperature in order to manufacture a component from that material. Does it make sense? I hope so. So if you look at the fracture surface of a material that has failed in a brittle manner, how do you know whether it has failed in a brittle manner or a ductile manner? So if your fracture surface is bright and shiny, please note, bright and shiny means brittle failure. Dull and not shiny means ductile material. And the other thing is that if your fracture has got very sharp edges and things like that, then it has failed in a brittle manner. Okay, so if you look at that 3.23 in slide 28, so this one in a low carbon steel, so a lot of dimples and things like that, that means it has failed in a ductile manner. So the process by which it fails in a brittle manner is called intergranular failure. So if the grains are giving way with respect to each other on each side, that means it can fail in a brittle manner. If it extends before it fails, that means it is a ductile failure. So when you are trying to deform a material, what type of failure would you like to have? What type of deformation would you like to have? You would like to have a brittle, no, sorry, if you would like to have a ductile deformation. You do not want the material to start deforming in the brittle regime. Does it make sense? Okay. So when you are trying to design your components, for those of you who have done senior design and things like that, you have to take into account how the material will behave, how the material will deform. Okay, so when you apply a normal load, it is called the mode 1 type of failure. If you try to shear the material, or if you try to if you're trying to push the failure areas against each other, that is called, it is called mode 2 type of failure, and the other one is a shear type of failure, which is mode 3. So among all these three, which one will show the least amount of load required for failure? Obviously mode 1. So which means that this failure load is taken into account for your design purposes, because this shows the lowest strength. So you would also like to, when you are trying to deform the material, you would also like to deform it in mode 1, but sometimes you will not be able to. The way you make the component, you may need to do shear deformation or mode 2 type of deformation. But this one shows the lowest load for the deformation or even the failure. So why are we trying to do all this? Where does all this play a role in the failure of a material? So depending upon the strength of a material, when it is in service, it can withstand a certain amount of load only, especially if the load is continuous and repetitive. Continuous repetitive loading is called fatigue loading. So if you have the wing structure of an aircraft, so it's going up and down would be considered to be a fatigue type of a failure. Take the example of a baseball pitcher. So he or she or softball pitcher, they are throwing the ball rotating the arm and throwing the ball. Okay, so they are applying a fatigue load to their shoulder. Okay, similarly, components are applying a fatigue load to the metal. I mean, to the metallic type of components. I mean, it can happen in the case of ceramics also, or a composite also. So when you look at the failure surface of one of these components, say a metal component or an alloy component, what is indicative of a fatigue type of load? If you see repetitive loads, like if you see these circular type of um, marks, these are called beach marks. Why do they call them beach marks? So if you go to the beach, um, the sea comes in and recedes back, comes in, recedes back. But the first time it comes to a certain distance, it doesn't come to the same um, distance the second time, and so on. So when it does that, it kind of um, pushes the sand a little bit and creates an up and down. So if you look at it from the top, you will see these kinds of repetitive marking that are parallel to one another, approximately parallel to one another. And so because they are found, those type of marks are found on a beach, so this is called beach marks or striations. So if you see these kinds of markings, then you can be almost certain that this component failed due to repetitive fatigue. And that fatigue can also be initiated on um, on a on an impurity or something like that. I don't know what happened. I have to stop this and start all over again.